I am a data engineer at Mercari. Mercari is a company that provides C2C online marketplace services based in Japan. In today's presentations, titled Integration of Batch and Streaming Data Processing with Apache Beam, I would like to introduce Mercari's publicly available OSS, Mercari Pipeline, and explain how data is processed at Mercari. Here is today's agenda. First, I will introduce Mercari Pipeline. Next, I will introduce the use of pipelines of stateful processing in Mercari. Finally, I will introduce our efforts to execute stateful processing more robustly by offloading state to external data store. Here is an introduction to data processing at Mercari. At Mercari, various data pipelines are developed and maintained, including batch data integration from various databases to data warehouse and other databases. Near real-time campaign perform promotions and fraud detections also used. As middleware for data pipelines, we use Cloud Data Flow and Apache Flink on Kubernetes to develop the pipelines. Mercari adopts a microservice architecture. Therefore, various teams develop and maintain their own services. As a result, various teams develop and operate their respective services. Microservice teams may need to develop and operate data pipelines as required. However, not all application engineers are familiar with developing or operate data pipelines. At Mercari, Go is often used for server-side application development, so there are not so many engineers who are familiar with Java and Scala, which are commonly used for big data development. In addition, each microservice often has its own databases, requires the handling of multiple types of large databases. For these reasons, we developed Mercari Pipeline as a tool to easily execute data pipelines without writing code. Mercari Pipeline is a tool for defining and executing Apache Beam pipeline in YAML or JSON format. This tool is available as open source software on GitHub repository. Define and combine the 6 options on the left side to define the pipeline. As an observant may have noticed, this concept is very similar to Beam YAML. This is because Beam YAML did not yet exist when we started development. If Beam YAML had existed at that time, we might have considered using it. The content of the option, 2 things are almost the same as those in Beam YAML. In options, define pipeline option. In sources, define the sources of data to process it. In transforms, define the content to be processed using the result from sources and the other transforms as input. In sinks, define the destination where you want to save the data from transform and sources. Sources, transforms, and sinks have predefined built-in modules, and you specify the parameter for each module. Sources and sinks have familiar predefined modules such as storage, JDBC, BigQuery, and PubSub, and such on. Transforms define modules that handle data processes such as BeamSQL, aggregation, and select, and some modules are defined for processing external data such as Bigtable. I'd like to explain these transform modules in more detail from this point on. The system option in Mercari Pipeline provides flexible settings for runtime configuration other than pipeline options. In args, various variables that you want to replace at runtime can be specified in the config file. By embedding built-in function in template text, it is also possible to easily embed settings such as today's date and time. Context is an option used to derive multiple processes from a single pipeline definition. As will be explained later, multiple pipelines that share common parts such as feature generation in ML, train, and predict can be simply defined as a single pipeline definition. Imports is an option for merging and using pipeline definition written separately at runtime. This is convenient when you want to manage independent pipeline definition individually. This slide explains examples of using the system context option. As shown in the example on the left side of the slide, each module has a tags field. These tags can be used to specify the context to which the module belongs. The example on the left defines a machine learning pipeline. During training, data stored in BigQuery is batch loaded to generate features, which are then saved to another BigQuery tab. During prediction, features are generated in real time from data retrieved by PubSub and streamed to another PubSub topic. The processing logic for generating feature is the same during both training and prediction. Defining the feature generation pipeline separately would make management complicated. In this example, the feature processing definition is small, but feature generation processing can be often be complex and voluminous. Therefore, we want to use context to enable switching between training and prediction using a single pipeline definition. For modules used in both training and prediction, specify both train and predict in tags. For other modules, specify train or predict as needed. When executing the pipeline, only modules with the tag specified in the system context will be enabled. In this example, we used a machine learning pipeline, but there are other use cases such as switching between scheduled regular execution and backfilling. Mercari Pipeline also includes pipeline development support tools. The support tools server provides functions such as pipeline verification, local execution, and deployment to the cloud via API and browser UI. Although still under development, it will be compatible with MCP server, enabling users to build pipeline while interacting with the MCP host application. This slide shows an example of pipeline definition using the UI of server, a development support tool. In this example, server is deployed to Cloud Run. The pipeline definition is described on the left side of the screen. In this pipeline definition example, questions are specified in the create modules, and the OnyxGen modules outputs the answer to each question using local LLM. The local LLM models is converted to an Onyx file using Gemma 3, uploaded to GCS and mounted to the path specified in the model parameter. The button in the upper right corner of the screen is used to evaluate and execute the defined pipeline. The dry run button does not actually execute the pipeline, but performs pipeline validation. The run button actually executes the defined pipeline locally on the server. Since it is local execution, it cannot process large-scale data, but it can execute small-scale processing without any problems. Whether it is dry run or run, the output schema of each module step is displayed when it succeeds. The launch button actually deploys the defined pipeline as a data flow job. The deployment project and region can be set as an environment variable in Cloud Run. Now, let's talk about the stateful data pipelines. This slide shows an example of real-time campaign conditions at Mercari. Customers who register as new members and participate in the campaign within 24 hours will receive points when they list an item within 24 hours after participant. They will receive 1,000 points for their first listing and 100 points for each the next 4 listings. To verify these conditions, 3 user events must be tracked in real time: user registration, campaign registration, and listing. This is an example of using Beam SQL module to evaluate this condition. Let's explain the SQL content. In the first query of with calls, with additional fields, we are extracting the fields such as timestamp for each type from the 3 types of events that have been combined into one using union for the subsequence processing. The next query, granted incentive, aggregates the 3 types of events for each customer and evaluates whether to grant incentives. To aggregate by customer, the group by calls specify user ID, but due to the trigger settings made earlier, aggregation is executed each time an event arrives. To evaluate the incentive grant conditions, the following aggregation results are specified as a filter in having calls. 1. Register for the campaign after signing up for membership. The campaign entry was made within 24 hours after registering as a member. The latest listing was made after entering the campaign, and the latest listing was made within 24 hours after registering as a member. This query evaluates whether the event is eligible for incentive allocation. The last query calculates the points to be awarded for events eligible for incentives. Whenever there is a listing that meets the incentive awards condition in granted incentive, we count the number of valid listings for each customer and award points according to the number. Beam SQL uses the aggregation processing result as a state for condition evaluation. Since the pipeline remained active through the campaign period, specify a global window and accumulate mode to retain the state. Specify a trigger to evaluate conditions for each event input. There are several issues within this approach of using Beam SQL to retain state as aggregation result. This is due to the fact that the order of event data is not retained when performing aggregation. Since the order is not retained, it becomes difficult to make order-dependent condition judgment. For example, it becomes difficult to determine whether a purchase was larger than the most recent purchase amount, or to make a judgment based on the total of the most recent 3 purchase amounts. Additionally, there is a possibility that the same processing result cannot be obtained using batch and streaming. Batch is used for pre-evaluation of real-time campaigns, such as simulation when and who become eligible based on past data. Unlike streaming, where processing generally arrives in the order of event time stamps, in batch, the order may vary widely. While setting trigger to watermark may yield correct final processing results, it is impossible to verify the process such as the timing of the determination. To resolve this issue, we can use the do-func state API instead of aggregation. Normally, do-func is a mechanism for processing input data in parallel individually. By using the state API, it becomes possible to update and retain the state each time input data is received. Additionally, state can be used independently for each specified key, such as user ID. In State API, various types of state are supported, but in cases such as this, ordered list state is useful. This is a type of state that can efficiently manage order based on the event time of the input data. Furthermore, by using the required time-sorted input annotation, it is possible to specify the input in order of event time in batches. This makes it possible to combine the processing result of batching and streaming. It is important to note that the state API cannot distribute processing as much as combine function. So if the data associated with the key is large, the processing load may become uneven and memory usage may increase. And using the state API with Dataflow Runner version 2 is not recommended due to performance issue. This is an actual code example of do function using the state API. In addition to the input data, it is specified to receive two states. One state is that retains the historical input data that is needed. The other is a state that retains the historical data up to a certain point in time that is needed. It is used to delete historical states that are no longer needed. Ordered list state enables data retrieval by specifying a time range. Here, we specify the oldest path time inferred from the processing content and the current event time. We use this path data to execute stateful processing. After that, we delete all data that is no longer needed from ordered list state and add new data. Mercari Pipeline provides stateful processing using this do function in select module. In the select parameter of the select module, you can specify the field name of the processing result, the processing function, and the range of path data to refer as a range parameter. If range parameter is not specified, processing will be performed on a per row basis as a user. The range parameter can be specified as either a number or a time span. The middle example calculates the sum of the result of the formula specifies the expression parameter for the most recent starting date point. In the next example of the lag function, range parameter is omitted, but calculations are performed by referencing path data with index. In this way, we can define processing such as window function. The following examples show how to perform time series prediction using stateful processing. Here, Kronos board, which is a foundation model for time series prediction, is converted to an Onyx file for use. Onyx is a machine learning model format that enables prediction processing built with Python to be executed in a runtime environment using other languages such as Java. This model predicts the next 64 points of data with a range of 9 quantiles based on the previous 64 points of data. Therefore, as input for this model, we use the array-arg function of the select module to create an array of data for most recent 64 points of the specified field value. The following Onyx modules input the array data into the Onyx model and outputs the prediction results. The mapping between the model input names and output names is also specified. In addition, since the prediction result of the model are outputted in 9 quantiles, specify the required range and quantiles as appropriate in the post-processing select. Here, the central prediction of result at the next point time are output as the field name forecast for 1. By applying the trained model using the Onyx module in this way, it is possible to run future generation and prediction on the same pipeline. So far, we have introduced an approach that retains state in pipeline processes. However, there are several issues with retaining state in the pipeline processes. In some use cases, it is necessary to retain state for long periods of time. Some campaigns may run for several months. Running for a long period of time also increases the risk of failure in pipeline. If a failure occurs, restoring the process requires recreating the state correctly. However, restoring a large amount of state is extremely difficult. Saving state snapshot also incurs costs. Additionally, modifying the content of state processing requires recreating the state from scratch. This increases the cost of change and makes modification more difficult. Therefore, instead of returning state within the pipeline processes, we will explain an approach that utilizes the data required for state calculation by storing it in an external data store. This slide explains the architecture for offloading state to external data store. We assume that user events are published from each microservice to a PubSub topic. We also assume that historical data for building state is stored in Bigtable. The data flow pipeline for logging writes user events received from PubSub to Bigtable. CDC data is generated from the written by Bigtable. The data flow pipeline for processing receives CDC and execute queries on Bigtable. Stateful processing is performed on the event historical data from the query result, and results are published to PubSub for integration. The data flow pipeline for processing executes query via CDC because it may utilize various user events. This is because the pipeline for logging is expected to be deployed as a separate pipeline since it receives events from each microservices. This slide explains the process of recreating a state from data in external data sources. When user events are written to Cloud Bigtable, CDC data is generated from Bigtable based on the written content. From this CDC data, a query is generated to fetch the data required for stateful processing. In this example, we retrieve user behavior history in time series. So the query is generated using the user ID and update timestamp from the CDC data. Cloud Bigtable supports SQL, so we embed the CDC data value in SQL format. Since executing query on Bigtable for each CDC data result in high load, we keep the query result in memory. Only data newer than the previous executed timestamp is retrieved and merged. Stateful processing is executed using the retrieved query results. This is an example of the config settings. The Bigtable module of transform is used for stateful processing. Use query parameter to define query retrieved from Bigtable for use in stateful processing. Embed CDC data parameter is in the query. In reality, CDC data is difficult to use in its original format, so we format it into a more usable form before embedding it in Bigtable. But we have omitted this explanation for purpose of this presentation. After that, the stateful processing is defined with the selected parameter in the same way as the select module explained earlier. Instead of returning state in the processes, retrieving history from an external data store and executing stateful processing simplify the internal state of the pipeline and make it easier to operate. On the other hand, retrieving historical history and reconstructing straight each time increasing overhead. We are currently considering a mechanism that produces the same result for both batch and streaming. We are currently working on enhancing stateful processing using external data sources, but basically it's necessary to use different mechanisms depending on the requirements. Here is a summary of today's presentation. We introduced Mercari Pipeline, a tool for defining and executing pipeline processing in YAML or JSON. Using content makes it easier to manage the definition on delivery pipeline. We introduced the example of using aggregation and do function state API as a method for performing stateful processing with Apache Beam. We also introduced an approach that offloads state retention to an external data store instead of the pipeline processes. Mercari Pipeline is still under development as OSS. Some of the features introduced today have not yet been included in the OSS version, but we plan to introduce them in a near future. We would like to share other interesting features that we were unable to cover today, such as an Onyx integration, at another opportunity. If you have any question or request, please feel free to contact us via the repository or social media. Of course, contributions are also welcome. Thank you very much for listening today.